Hi, grade 10s. I want to start this video by referring you to the textbook from Siavula and balancing chemical equations. Now, it's very important to realize that in order to balance chemical equations, you have to understand the conservation of mass, because the number of, or the mass of the reactant particles before must equal to the mass of the reactant products after the reaction. It's because the atoms are rearranged to form a new compound. So looking at this example of iron with sulfur, an iron atom has a relative atomic mass of 55,8 and sulfur has a mass of 32,1. An iron sulfide particle has a mass of 87,9. So the mass of the reactants is equal to the mass of the products. And the equation is always the simplest ratio. Here is another example to show the conservation of mass. If we have 16 grams of methane and 64 grams of oxygen, it produces 36 grams of water. How much carbon dioxide is produced? Just by the conservation of mass, you can work out that you need 44 grams of carbon dioxide to be produced. So balancing chemical equations relies on the conservation of mass and the law of conservation of mass. Now, using the conservation of mass, we're going to look at how to balance a chemical equation. Remember, a chemical equation is the symbolic representation of a chemical reaction, and the reactants are always given on the left-hand side and the products on the right-hand side. The arrow connects the two, saying that these reactants form this product. And the law of conservation of mass states that no atoms can be created or destroyed in a chemical reaction, but they are rearranged. So the number of atoms present before must equal to the number of atoms afterwards. So let's look at this with propane burning in oxygen. Okay. As you saw, the first thing to do is let's choose one element. So let's take the carbon, for example. Okay. I write down all the atoms that are present before and afterwards. So there are 3 oxygen atoms there, 3 oxygen atoms there. So we can see they're not balanced. Okay. I'm going to start with carbon because it's the one that appears in one molecule only. So I have 3 carbons in the reactants, and I only have 1 and with the product. So the easiest way is to say, well, 3 carbon dioxide molecules must be formed. Now my carbons are balanced. But now because I've got 3 carbon dioxide, I have 7 oxygen atoms. Okay, so the oxygen atoms are not yet balanced, but the carbon atoms are. So now let's look at the hydrogen. There are 8 on the reactant side, but only 2 on the product side. So if 4 water molecules are formed, that will give me 8 hydrogens. The hydrogens are balanced, but now I have 10 water molecules because 4 plus the 6 is 10. So the oxygen is not balanced on the other side. The only way I can get 10 oxygen atoms on the other side is if I have 5 oxygen molecules. If I have 5 oxygen molecules, then the equation is balanced. I've got 3 carbons, 8 hydrogens, 10 oxygens, 10 oxygens. The equation is balanced. So this is the traditional method to balance chemical equations, where you learn to do it by feel. But how do you get to that stage? This is what this activity is for. So I'd like you to go to the worksheet now and do the first part where you have to fill in the number of atoms in that table to see if you can balance the chemical equation. Now, you could also try this PhET simulation on balancing chemical equations and start firstly with the introduction. I'm not going to use any of the tools, but let's say I've got a nitrogen molecule. Okay, I know if I've got 1 nitrogen molecule there, then I must have at least 1 ammonia in my reactants. But that now gives me 3 hydrogens. And because I've got 2 nitrogens on the reactant side, I must have at least 2 ammonia. And that tells me then that I must have 3 hydrogen molecules reacting, and there my equation was balanced. Here, if I want to break up water, 1 water molecule will form at least 1 oxygen molecule. But you can see in the water molecule, oxygen molecule needs 2 oxygens, so I need 2 waters. If I have 2 waters, I will have 4 hydrogen atoms, in other words, 2 hydrogen molecules. Now the same with burning methane in oxygen. Methane is CH4. It will form at least 1 carbon dioxide molecule and 2 water molecules, which therefore mean I need 2 oxygen molecules. So you can play with the PhET simulation and learn how to balance chemical equations. So there's a game that you could play. So this is level 1. If I have hydrogen and I have oxygen, it will form water. So playing with the PhET simulation, if I have I must have one oxygen molecule will form 2 water molecules. If I have 2 water molecules, I will need 2 hydrogen molecules, and you can check and it will tell you whether you've balanced the equation or not. Here's another example, PCl5. I've got 5 chlorines, only 1 phosphorus. So very simple to balance. It's a 1-to-1, but because Cl2 is a diatomic gas, so remember it will be Cl2. Now you can try with sulfur trioxide, which breaks up into sulfur dioxide and oxygen, and you can play through this game and you can learn to balance chemical equations. And it will tell you if and when you are wrong and where you've made a mistake. So I made a deliberate mistake here just to show you that if I press check and I'm not balanced, then it will tell me that I need to try again. So go to the PhET simulation and play and see how you become accustomed to balancing chemical equations. And here's the last example. I did hydrogen chloride will break up into, remember, both hydrogen and chlorine are diatomic, so I will need 2 hydrogen chloride molecules. So great, hence to end this explainer video, I'm going to show you a video that shows you how to balance equations just for additional reinforcement. When you've done that, you can go and complete the worksheet and try and balance all those chemical equations using the particulate diagrams to help you out.
In this video, you're going to learn how to balance chemical equations. The law of conservation of mass states that no atoms are lost or made during a chemical reaction. They cannot be made from nothing, and they cannot vanish into nothing. If you don't believe me, you try making an atom from nothing. The number of each kind of atom remains the same during a chemical reaction, even though they might arrange themselves differently in compounds. So here there are 6 oxygen atoms, and here, and here. But these are 3 different ways of arranging the atoms. Chemical reactions are all about rearranging atoms. Chemical reactions can be represented by symbol equations so long as the number of atoms on each side of the equal sign remains the same. Often, when you write out chemical reactions, the atoms do not balance straight away. You need to balance the equations to conserve atoms. You do this by putting numbers in front. Here, we start off with 3 O2 molecules, 6 oxygens overall. In the formula, you can work out how many atoms there are by doing 3 times the subscript, or little number, on the oxygen, which is 2. 3 times 2 is 6. Then we make 2 ozone molecules. The subscript is now 3, so the number at the front has to be 2, so that something times 3 is equal to 6. The big numbers at the front change everything in the formula, whereas the small subscript numbers only change the element they follow after. Until you are really familiar with using formula symbols like this, it's much easier to draw out the molecules in full, as we have done here. So Na2O has 2 sodium atoms and 1 oxygen atom, whilst SnO2 has 1 tin atom and 2 oxygen atoms. If you have 2 Na2O, you have 2 times 2 sodium atoms. That's 4 sodium atoms. But you only have 2 times 1 oxygen atoms. How many oxygen atoms are there in these compounds? Pause the video for a moment. Ready? Remember, if there is no number next to it, there's just 1, not 0.